Welcome back to Discrete Differential Geometry. Today we're going to embark on a journey to learn a language called exterior calculus that we will use to talk about geometry in both the mathematical and the computational setting, starting today with something called exterior algebra. Now, before we start on this journey, a very reasonable question to ask is, why should I bother? Why should I learn a whole new language for talking about geometry? Maybe I already know vector calculus, I already know other pieces of mathematics. Why learn exterior calculus as well? And here is perhaps the most important motivating example. Okay, so maybe some of you know what this means, many of you may not. What does this statement say? What does it mean? Does it contain useful information? Does it give you some insight that you didn't have before? Well, if you don't speak this language, or in this case the language is Japanese, you may never know. Right? So in this case, what this says is, コンピュータサイエンスの建物の地下では銀があります. What does that mean? It means, well, actually, it's telling you there's gold hidden in the basement of the computer science building. That could be a useful thing to know. You just run down there and grab some gold, right? And in general, the point is that language is very, very important because it lets you communicate with people who know things that you don't. Why learn exterior calculus? It's not necessarily because it's the best language, right? Or it's the most important one, but rather because there are already a huge number of people who speak this language and have lots of deep insights about geometry expressed in this language. So just like people can get really religious about programming languages, people can get really religious about mathematical languages. Oh, you shouldn't use exterior calculus. All you need is vector calculus. Or you should write everything in tensor notation in local coordinates, or whatever. The answer actually is that you should try to speak as many languages as possible so that you can communicate and work with as many people as possible. So in this course, we are going to focus on exterior calculus, but I'll highlight at various moments other ways you can look at geometry and talk about surfaces and manifolds and so forth. There are, of course, certain idiosyncratic benefits to using any particular language. Not all languages are created equal. So just as another motivating example, right? Everything in mathematics, for instance, can be expressed in the language of, let's say, sets, points and sets, and maybe some predicates, right? So here, for instance, is an excerpt from Russell and Whitehead's Principia Mathematica, where they say all sorts of interesting things to conclude only that, well, 1 + 1 = 2, right? So depending on what task you're interested in, certain languages may be more or less efficient for that task. It's generally wise to try to find a language that's appropriate for the domain that you're working in. So with that in mind, why learn exterior calculus in particular if you want to do geometry and if you want to do discrete and computational geometry? Well, one reason is that it's a very natural language for talking about signed volume. A lot of the quantities that we need to work with in geometry and math and physics will be something about a length or an area or a volume, and also something about orientation. Are you going in or out? What's the direction? So we already talked a little bit about orientation when we looked at oriented simplicial complexes. Exterior calculus shows up all over modern geometry, so it shows up in algebraic geometry. It shows up in a distinct subject called geometric algebra. So if you've heard of Clifford algebra, or you're a physicist interested in the behavior of spin, more broadly in physics, exterior calculus helps to make very clear distinctions between quantities that have no mass, like velocity and acceleration, and those that do have mass, like momentum and force. And in fact, exterior calculus is the starting point for a whole field of geometric mechanics, looking at the physical world through the lens of geometry. In this class, we're going to put a special emphasis on computer science, on computation, and doing geometric computation on meshes. And exterior calculus will turn out to be a very natural language here because the mesh elements we've studied, K simplices, turn out to have a very natural correspondence with the objects we're about to study called K forms. Okay, so more broadly, where are we going? So our goal is to build up this idea of discrete exterior calculus, and in a nutshell, discrete exterior calculus kind of replaces vector calculus, replaces pen and paper expressions with computation on meshes. To make sense of all this, well, you'll need to know already a little bit about linear algebra. You'll need to understand the behavior of little vectors in Euclidean space. How do they add and so forth? And you'll need to know already a bit about vector calculus. How do vectors change over space if we have a vector field, for instance? We'll make reference to these ideas quite a lot. Starting with those ideas, in the next few lectures, we're going to build up an understanding of exterior algebra. So we're going to generalize linear algebra a little bit by, instead of working with just kind of these one-dimensional vectors, things that have higher dimensional volume. Okay, and we'll also have an analog of vector calculus, or a generalization of vector calculus, called exterior calculus, which says how do these little volumes, or K vectors, change over space. Finally, once we have a good handle on that, we can think about how to translate this into meshes and algorithms. How do we do all of this on a mesh? Okay. Why are we going there? Why do we want this language on meshes? Well, because we want to do cool and useful stuff. We want to implement useful mesh algorithms. So a lot of geometry processing algorithms are really centered around solving certain kinds of equations on meshes, like partial differential equations, or PDEs. Meshes are made up essentially of little volumes of different dimension, right? Edges, and triangles, and tetrahedra, and so forth. So if we want to solve equations on meshes, then we're going to need to translate, or in our case, integrate equations over these little volumes in order to turn our smooth, continuous objects into finite objects on which we can do computation. Okay? Once we have our hands on these basic tools, we can build up some additional algorithmic components that can be reused for many different geometry processing algorithms. Here are a few that we'll go into in more depth later on in the class. And once we have those basic computational tools in place, finally we can implement some applications. We want to smooth out some geometry, or find the distance from point to point, or flatten out a surface in the plane, whatever it is we need to do. Okay, but let's start at the very beginning. And let's just remember a little bit about linear algebra and vector spaces. In fact, let's go back even further and try to understand something very, very basic, but in a slightly deeper way. So here's a question. It might seem like a kind of ridiculous question, but can you answer it? So the question is, why does 3 times 4 equal 4 times 3? Why is that true? You know that it is true, but you may have not stopped to really think about why it's true. And I think there's a lot of very complicated answers you can give. Like you could say, if you've studied a little bit of algebra, you'd say, well, because it's abelian. Well, that's not really saying anything about why. That's just regurgitating the fact that it's true. 3 times 4 is equal to 4 times 3. Multiplication is commutative. It's the same thing. You might also just say, well, why is 3 times 4 equal to 4 times 3? Because that's the rule, because that's what I was told. And that's not a very good reason. There are good reasons why all these rules are true. In this case, there's a very good geometric reason. We can draw a simple picture. Can you think of a picture you could draw to justify why maybe we want 3 times 4 to be the same as 4 times 3? Well, here's a good picture. 3 times 4 could be saying, well, I have an object, a rectangle, that has one side length equal to 3 and one side length equal to 4, and the product of these two side lengths is the area. And so if I have another rectangle where the first side length is instead 4 and the second side length is 3, well, I have the same area. Okay? So the fact that we allow the two terms in this product to be swapped is just saying we would like, please, a rule for numbers that captures the natural behavior of areas and lengths. Right? We didn't have to define multiplication this way. We did it because it was useful in modeling something that we care about. Okay? And the real point of giving this kind of, simple example is to just emphasize the fact that you should never accept a rule purely on faith. You should always be asking, why is this the rule? Where did it come from? What motivates or justifies defining this object or this operation this way? And I promise you that if you keep asking this question as we go through this course and we learn about this new language, you will have a much better understanding of what's going on than if you simply plug and chug, than if you simply memorize the rules and then reapply them later. Okay? So let's go a little more advanced and talk about vector spaces. So first basic question is, what is a vector? Right? What picture comes to mind when you think of the word vector? How would you explain this to somebody else? So there are a lot of good pictures. One pretty good picture is an arrow. Right? A vector in Rn, in 2 or 3 dimensions or n dimensions, you can draw that as a little arrow. What's another example of a vector or kind of a picture of a vector that you could draw? Well, one that might be a little less familiar is a function. Right? Functions and little arrows behave in very similar ways. I can add 2 arrows and get another arrow. I can add 2 functions and get another function. I can scale an arrow up by a number. I can scale a function up by a number. And if you keep going through the properties of vectors, you realize that these really aren't so different. Right? Functions are perfectly good examples of vectors. Collections of functions are examples of vector spaces. So when we do geometric computing, or geometry, we often care most about dimensions 1, 2, 3, usually pretty low dimensions if we're talking about objects in the world we live in, and also infinity. We care about functions which can't be specified using just a finite number of points. Okay? So it's a little abstract. Let's get a little more concrete. So what is a vector space more formally? Well, formally, a vector space is a set V together with the operations of addition, which take 2 vectors and produce another vector, and scalar multiplication, which takes a number and a vector and produces another vector. These operations have to satisfy some rules for all vectors x, y, z and scalars a, b. In particular, x plus y has to be the same as y plus x. Adding x and y first and then z has to be the same as adding y and z first and then x. There's always a 0 vector such that adding it to any vector just gives you that same vector back again. There's always, for any vector x, some other vector x tilde such that adding x and x tilde gives you 0. So x tilde is kind of the opposite of x. And so on. There's rules for how scalars interact with vectors. Okay. And by the way, we're just going to talk for now about real vector spaces, but in general, you could use complex numbers as well. Okay, so there's a big long list of rules, right? Why are those the rules? Because I said so. Well, that's not a good reason. We really want to understand why are these the rules? Where did they come from? What do they capture? So as with our discussion of numbers, the rules for vector spaces reflect how certain objects, oriented lengths or little arrows or whatever you want to think about, behave in nature. Okay? So first of all, what does it even mean to say that if I take two vectors and I add them, I get another vector? Well, we could perhaps draw a little picture like this. If we walk along x and then we walk along y, we get another vector, x plus y. Why might it be then that x plus y is equal to y plus x? Oh, well, because if I first walk along y and then I walk along x, I get the same vector. How do I know that every vector x has an opposite or an additive inverse? Well, if I walk along x, I can just walk back the other direction and get back to 0. Okay? And so on. And so hopefully for each rule in that list, you can draw a little picture involving arrows and talking about adding and scaling to convince you that these rules capture something useful, something that I actually care about talking about. Now, at some point, you start drawing these pictures. Okay, why do I have associativity of addition? And the picture becomes a mess. And at that point, you realize, okay, there is some value to having these algebraic expressions. The reason we want to translate these pictures into some nice notation is that it lets us do some very complex manipulations, right, without having to think about some image in our head all the time. Okay? But it's still very, very important before you start manipulating symbols to understand, what are you doing with those symbols? Why are you doing it? What do the rules mean? And this is going to be especially true for exterior calculus. One other important concept that we want to review from linear algebra is the idea of an inner product. So we can also associate a vector space with an inner product. We're going to write inner products like this. We're going to use these angle brackets. Okay, you stick two vectors into those angle brackets, and it's going to give us a real number. Intuitively, this quantity inner product of x and y captures how well two vectors x and y sort of line up. Do they point in the same direction? Do they point in different directions? And also something about their magnitudes. The bigger the vectors get, the bigger the inner product gets. More precisely, for all vectors x, y, z, and v, and real numbers a, any real inner product must satisfy, well, a symmetry property. X inner product with y is equal to y inner product with x. Linearity. So if I scale x by a factor a, that's the same as scaling the inner product. If I add two vectors in one of the arguments of the inner product, that's the same as just taking two separate inner products and adding them together. And positivity. An inner product of a vector with itself is non-negative, and it's 0 only if x is equal to 0. Okay, yet another list of rules. Where do these rules come from? Why might they be natural? Why did somebody long, long ago decide to define them this way? Okay, well, again, if you don't understand, if you don't really deeply understand why these are the rules, try drawing a picture for each rule. So for instance, for symmetry, why is it that x inner product y is the same as y with x? Well, we said that we kind of want to capture the idea of how much these two vectors line up with each other. It shouldn't matter which one we specify first. If we renamed x to y and y to x, we should get the same result. Okay, I'll let you draw the rest. A very important example of an inner product is the Euclidean inner product, which just says if I have two vectors x and y specified by coordinates x1 through xn and y1 through yn, then the inner product is just the sum of the products of all the coordinates. Okay? All right, so that's it for review, and now we can move on to something new and interesting, the wedge product. So the wedge product is the thing that's going to let us start with the vector calculus that we know and love and start building up kind of higher dimensional objects than just ordinary one-dimensional vectors. A good analogy to think about here from linear algebra is the idea of the span. Right? So geometrically, what was the span of two vectors? Okay, well, if these two vectors are, let's say, in three-dimensional space, you might imagine that the span gives us the whole plane of points in that space that we can get to by walking some distance along u and then walking some distance along V. So more precisely, if U and V are elements of a vector space capital V, then the span of U and V is all the vectors x in V that can be written as AU plus BV for constants A and B. Okay? More generally, in any vector space V, the span of a finite collection of vectors V1 through Vk is the set of all possible linear combinations. So span of V1 through Vk is equal to all the vectors x in V, such that x can be written as the sum from I equals 1 up through k of ai, vi for some scalars ai. The span of a collection of vectors is what's known as a linear subspace, right? A subset that forms a vector space with respect to the original vector space operations. Right? All this is saying is, if I have two vectors in this span now and I add them, they're still in the span. Right? You should be able to show that pretty easily given the expression we have for the linear combination. Okay, so this is all review. By the way, if this sounds unfamiliar to you, please go back and look at your linear algebra textbook or wherever you learned linear algebra and make sure that you have a reasonable understanding of this concept. Okay. So the wedge product, which is part of exterior algebra, is going to be something like the span, very similar in a way. We start out with a couple vectors, u and v, and they define, well, rather than a whole plane, they define a little piece of a plane, which we're going to call u wedge v. Okay? So u wedge v is the wedge product of u and v. Now, very, very important, very different from span. If we shrink one of the vectors, let's say we make u a little bit shorter, we're actually going to get a different object. We're still going to get a little piece of the plane, but now it's a smaller piece. Whereas with the span, it doesn't matter. The length of the vectors doesn't matter for the span, only their direction. Another really, really important difference between the span and the wedge product is this little piece of the plane has an orientation. When we do u wedge v, in this case, the orientation points up. If instead we did v wedge u, the orientation would point down. And for this reason, we write just notationally that u wedge v is equal to minus v wedge u. They have different orientations. Okay? So the key difference between span and the wedge product is that the wedge product gives us an orientation and a sort of finite extent. And we can also see that it has a kind of anti-symmetry property. If we switch the order of the arguments to the wedge product, we get minus what we had before. The other important difference is, what is the object coming out of this operation? So when we took a span of vectors, we got a linear subspace. Right? We got another vector space sitting inside our original vector space. What we get with the wedge product is not a linear subspace, but rather something called a k-vector. So in this case, we wedged together two vectors, so we get a 2-vector. Okay? We'll be a bit more precise about k-vectors in a little while, but at least now we have a name to work with. All right. One very important special case is what happens when you wedge a vector with itself. So if I do u wedge u. So what do you think happens here? Well, one good analogy you could draw is to say, what happens if I take a span of the vector u and the vector u? Right? Even though I'm taking a span of kind of two things, I still get a one-dimensional linear subspace. There's something kind of degenerate that happens. So with a wedge product, if I wedge u and u together, I'm still building a little parallelogram, a little 2-vector, except that this parallelogram has 0 area. Right? We said that the wedge product is going to capture a notion of orientation and a notion of area. So we can write u wedge u is equal to 0. Okay, really important identity. We'll use this all over the place. And just a tiny footnote that we're going to generalize things a little bit later on in the course. It won't always be the case that u wedge u is equal to 0, but for the next few lectures, this is a very safe assumption. Okay. What other things can we say about the wedge product? What rules naturally follow from this idea that the wedge product is being used to build up little k-dimensional volumes? Well, so far we've been talking about wedging together just 2 things. What happens if we wedge together 3 things? Okay, so if I take u, I wedge it together with v, I get a little parallelogram. Well, if I wedge this together with a third thing, let's say w, a third vector, then I get something like this. U wedge v wedge w now gives me a parallelepiped. Okay. Well, what happens if I do this in different orders? So one thing I could do is I could wedge together u and v first, and that would give me a little parallelogram, u wedge v. And then I could wedge it with w to kind of extrude that parallelogram along the w direction to get my parallelepiped. Is there another way I could do this? Sure, I could first wedge together v and w, and then I could extrude that along the direction u, and I would get actually the same parallelepiped. Right? And so for that reason, we might say, yeah, a reasonable rule would be to say that u wedge v and then wedge w is the same as u wedge, well, quantity v wedge w. Right? That's why we'll have associativity in our wedge product. It's because it says something natural about the way we build up volumes from vectors. Okay. What else can we learn about the wedge product by playing these little games? Well, here's one thing we could do. Let's say we have a wedge product of a vector u with some vector v1, and then we have another wedge product, u wedge v2. So we have these 2 vectors. If I put these together, if I join these together, well, it's not a parallelogram, right? But can we find a parallelogram with the same area by just wedging together a couple vectors? Sure, we could instead wedge u with v1 plus v2, and we'd get another little parallelogram, and you can argue to yourself pretty easily that this will have the same area as the union of the first 2. So for that reason, we might like to write u wedge v1 plus u wedge v2 is equal to u wedge v1 plus v2. Okay? So as I mentioned earlier, it's important to give a name to these objects we're building up with the wedge product, and that name is a k-vector. So the wedge of k-vectors is called, amazingly enough, a k-vector. Right? So if we wedge together a vector u and a vector v, we get a 2-vector u wedge v. If we wedge together vectors u, v, and w, we get a 3-vector u wedge v wedge w. If we wedge together just one vector u, well, we get a 1-vector called u. And in fact, we can also just wedge no vectors together, and we'll get a 0-vector. Okay, we'll talk about exactly what that means in a second. It's still a useful concept. But before going any further, I want to make a very, very important point about these pictures that we've been drawing. Right? So we've been drawing k-vectors so far as these little parallelograms, but this visualization is actually a little bit misleading. Right? A k-vector really only encodes 2 pieces of information. It encodes a direction and it encodes a magnitude. Okay, so the right way to interpret these pictures is to say, okay, if I see 2 parallelograms and they sit in the same plane and they have the same orientation, like up or down, and they have the same area, well, then they represent the same 2-vector. So all 3 of these little drawings, these little parallelograms, are really just trying to evoke the same 2-vector. So basically what we're saying is if you wedge together u1 and v1, and then you wedge together u2 and v2, and you find oh, those have the same area, they sit in the same plane, they have the same orientation, then those are the same 2-vector, right? Likewise for U3 and V3. So what we might say, we can kind of define 2 vectors as saying, oh, well, 2 vectors are sort of equivalence classes of parallelograms that have the same area, sit in the same plane, have the same orientation. Or more generally, we might think of a 2-vector in 3-dimensional space as just some little patch of surface that has a given area and a given normal direction. Okay? So these parallelogram drawings are meant only as a helpful mental model, and quite often it is a perfectly good way of thinking about what's going on. Okay. Also very important to think about this degenerate case of what do you get when you wedge no vectors together? What does this look like? What is the picture that you would draw? Well, you basically get this. Right, there's the picture. Okay, well, maybe not quite, because we said a k-vector has a direction and a magnitude. When we have something 0-dimensional, it doesn't really have much of a direction, but we can still give it a magnitude. Right? So we can say a 0 vector is something that only has magnitude. What we're really saying is a 0 vector is the same thing as a scalar value. Right? A 0 vector is just a number. And this fact just helps unify everything in a nice way. It makes sure that everything works out nicely as we start manipulating k-vectors in general. Okay, so the key idea is a 0 vector has a magnitude but no direction. All right. So the wedge product was one of our basic operations in exterior algebra. It lets us build up these bigger volumes from vectors. Our other basic operation is something called the Hodge Star. And here again, we have a useful analogy from linear algebra to help us understand what is the Hodge Star all about. That's the idea of the orthogonal complement. So geometrically, what is the orthogonal complement of a linear subspace? Is this something you remember from your linear algebra class? Well, here's one little example. I could consider the orthogonal complement of a span of 2 vectors. So let's say I have 2 vectors u and v, and if I take the span of these vectors, I get a whole plane, right, extending off to infinity. I'll call that capital V. If I take the orthogonal complement of v, well, that's going to give me all the vectors in Rn that are orthogonal, or whose inner product is equal to 0 for all vectors w in the vector space V. Okay, we can write that maybe as V perp. In 3 dimensions, for instance, if I have this 2-dimensional plane, then the orthogonal complement is a line orthogonal to that plane. Now, by the way, one important thing to notice is that unlike the span or the wedge product, we now need some additional information to define what the orthogonal complement is. We need to pick a choice of inner product. Right? So the inner product is something that has to satisfy certain basic properties. The dot product is one example, but there are a lot of different inner products we could choose. Okay? And that will be important when we start talking about geometry and curved spaces. The different inner products will do different things for us. Okay. But for now, we can just think of this as the dot product in Rn. Okay. So more precisely, we can say let U be a linear subspace of a vector V with an inner product given by these angle brackets. The orthogonal complement of U is then the collection of vectors U perp, defined as all vectors V in capital V, such that the inner product of little u with little v is equal to 0 for all little u's in big U. What is the motivation behind the orthogonal complement? Why do we want to specify a linear subspace as a complement? Why don't we just, I don't know, describe it as a span? We just give vectors in that space and say that the space is the span of those vectors. Do we need this notion of orthogonal complement at all? Well, here's a good example to motivate why you ever want to specify something in terms of a complement. I can ask you this question. What kind of cuisine do you like? What kind of food do you like? Okay, this is a very, very important question. And one way you could answer it is to just start rattling off every kind of cuisine you like. I like Vietnamese food, and I like Italian food, and I like Ethiopian food, and I like, the list could go on and on and on. Hopefully it does. There's a lot of wonderful food out there in the world. But this would take you a long time to specify the answer. So another thing you could do, if you're a real connoisseur, is you could say, actually, I like everything out there except for Bavarian food. You could specify what you like by giving the complement of the things that you don't like. Right? And that's typically why we have this kind of construct in a language, because it's often easier to specify a set by saying what it doesn't contain than what it does. Okay? And that's kind of the idea behind the Hodge star. It's something like an orthogonal complement. Why do we bother with it? Well, because in many cases, it's going to be easier to specify something by talking about its complement rather than the thing. Okay, we'll see that this is a very natural idea geometrically. So if we start out with a 2 form, for instance, one way to specify that is to say, well, it's the wedge of 2 vectors u and v. It's u wedge v. Right? And those 2 vectors together with their lengths and the order that we do the wedge product tells us everything about the size and orientation of this 2 form. But we could provide that exact same information by just giving one vector, w, and saying my 2 form is orthogonal to this vector, and this vector encodes the direction and magnitude of the 2 form. Right? And the Hodge star is just an assertion that says these 2 different pieces of information encode the same 2 form. Right? They encode the same little parallelogram. So star of u wedge v is equal to w. Just like the orthogonal complement, that means the Hodge star is always taking a k-dimensional thing and giving us an n minus k-dimensional thing, with, again, the important distinction that we now have a notion of orientation and magnitude that we didn't have with the orthogonal complement. There's another important detail that we have to pin down in order to really say what the Hodge star is. So one thing you might say at this moment is, wait a minute, can't I also express the same 2 form using minus w instead of w? And so how do I know that star of u wedge w is equal to plus w or minus w, or what do I do? And so, as we said we'll do many times in differential geometry, we have to pick a convention. And the convention here is that whenever I take a k-form z and wedge it with the Hodge star of itself, I get something that's positively oriented rather than negatively oriented. Okay, and that's enough to pin things down. Concrete example is the Hodge star in 2 dimensions. And a really good analogy here is a 90-degree rotation. Okay, so for instance, if I have a vector u, let's say pointing east, then what is the Hodge star of u? Well, we know that it has to be something orthogonal to u, right? But which direction? Do we go counterclockwise or do we go clockwise? Well, the answer is we have to pick a convention. And our convention is going to be that the star of u is a 90 degrees counterclockwise rotation. Okay? So in 2D, this is a really concrete meaning. What do you think happens if we now apply star again? What is star u? Okay. Well, it certainly seems important that we stick with the same convention we had before, right? We just said that star u is a counterclockwise rotation. So we probably shouldn't go back to u. Better would be to say star u is kind of minus u, right? So this is, again, a little bit different from the orthogonal complement. if I take the orthogonal complement of the orthogonal complement, I always get back to where I started. But if I take the Hodge star twice, I might get minus what I started with, because I have now this notion of orientation that I didn't when I was talking about the orthogonal complement. Okay? And if we apply the Hodge star a third time, we have star, 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 u, we get, well, minus star u. We do another 90-degree rotation, and if we do this one more time, we go back to u, and around we go. Okay? So just to recap, the whole idea of exterior algebra is we start with a vector space V, let's say it's n-dimensional, and this vector space contains just ordinary vectors, which now we're giving a slightly fancier name, a one vector. Okay? We can wedge together k of those vectors to produce a k vector, which is kind of a little signed volume, a little oriented volume. We can also apply the Hodge star to get the complementary k vector. Those are our two basic operations, wedge product and Hodge star. As usual, we have all the ordinary operations that you'd have in a vector space. Right? We can add together k vectors, we can scale them by numbers, and this just behaves in the way that you would naturally expect in any vector space. What does it mean to scale a 2 vector by a factor of 10? Well, that just means the area gets bigger by a factor of 10. Okay? Yet another place where if you don't feel comfortable with the rules, with what's going on, sit down and try to draw out little pictures. What do all the vector space operations now mean for k vectors? Another way to make this all very concrete is to use a coordinate representation of k-forms. You might have noticed that so far we haven't talked at all about coordinates. We haven't given components to our vectors. We haven't given components to our k-forms. And there's a very good reason for this, which is that the geometric meaning of k-forms doesn't depend on writing them in coordinates. The geometric meaning of vectors in linear algebra really has nothing to do with coordinates. You can really confuse yourself by thinking that a vector is a list of numbers. It's not. Right? A vector can be represented using numbers, but it's not fundamentally a list of numbers. And that's certainly true when we think of vectors that are, let's say, functions rather than little arrows. Okay, it is, however, of course, extremely useful to be able to work in coordinates if we want to do concrete calculations. So let's go ahead and do that for k-forms. Okay, so first let's recall, what is this idea of a basis all about? And here's a perfectly good mental image. I have a vector v in the plane, and to specify that vector, I can choose some pair of coordinate axes, e1 and e2, and I can simply measure how far does the vector v go along the axis e1 and how far does it go along the axis e2, call those v1 and v2. And then v is the vector that I get by starting at the origin, walking a distance v1 along e1, and then walking a distance v2 along e2. Okay, so that's the idea. We can encode a vector by its extent along a collection of independent axes. A little more precisely, okay, let's say that V is a vector space. A collection of vectors is called linearly independent if no vector in the collection can be expressed as a linear combination of the others. We talked about that when we talked about convexity. A linearly independent collection of vectors, e1 through en, is called a basis for V if every vector in V can be expressed as V equals v1 e1 plus v2 e2 plus ... plus vn en for some collection of coefficients v1 through vn. Okay? In other words, it's a basis if every vector can be uniquely expressed as a linear combination of these vectors, these basis vectors. In this case, we would say that V is finite dimensional with dimension n. Every vector can be expressed using just n coefficients, so it's finite dimensional. All right. How do we talk about bases for k vectors? What does this mean? Well, the key idea is that, as with ordinary vectors, signed volumes can be expressed as linear combinations of little basis signed volumes or basis k vectors. So to make this concrete, let's just work in R3. In R3, we might have three basis vectors, E1, E2, and E3. Okay. What are our basis 2 vectors going to be? If I have basis 1 vectors, how might you think about constructing basis 2 vectors? Well, we actually only have one way of making 2 vectors, which is to wedge together 1 vector. So how about we wedge together our basis 1 vectors, and we'll get some other 2 vectors, E1 wedge E2, E2 wedge E3, and E3 wedge E1. What about basis 3 vectors? Well, same idea. We can wedge together, let's say E1 wedge E2 wedge E3 to get a basis 3 vector. Okay. We haven't really convinced ourselves yet that these are bases. Do they span the whole space of 2 vectors? Right? What's going on here? So one useful thing to think about is, like, how many basis vectors do I have for a given kind of K-form? What's my dimension? So let's this time consider a vector space V that's 4-dimensional, R4, and give it a basis E1, E2, E3, E4. So question for you to answer: how many basis 2 vectors do I have in this case, assuming that I get my basis 2 vectors by wedging together my basis 1 vectors? How many basis 2 vectors do I have? Well, I claim that you have 6, and here they are: E1 wedge E2, E1 wedge E3, E1 wedge E4, E2 wedge E3, E2 wedge E4, E3 wedge E4. Why? Why only these? Wait a minute. Aren't I missing some important pairs? Like, couldn't I wedge together E3 and E2 to get another basis 2 vector? Couldn't I wedge together E4 and E4? Right, so this is a moment where it's really important that you not just think of these as symbols on the page, but you try to remember, what does this wedge product mean geometrically? Right? What properties does it have? Well, let's think about E4 wedge E4. What did we say happens if you wedge a vector together with itself? Right? You get a parallelogram that has 0 area. E4 wedge E4 is equal to 0. And so this really doesn't sound like a useful basis 2 vector. Moving along 0 doesn't take me anywhere. Okay, so that's out. What about E3 wedge E2? Why is that not in my list? Okay, well, we had another very important property, which is that U wedge V is equal to minus V wedge U. Right? This anti-symmetry of the wedge product. If I swap the arguments, I get the opposite orientation. And so if I put E3 wedge E2 in my list, I'd have something redundant, right? Because E2 wedge E3 already captures that basis direction. I can multiply E2 wedge E3 by minus 1 to get that same 2-vector E3 wedge E2. Okay? So there really are only 6 basis 2 vectors in this case. How many basis 3 vectors do we have in this case? Maybe using the same kind of reasoning. What do you think? Okay, well, I claim that there are 4. E1 wedge E2 wedge E3, E1 wedge E2 wedge E4, E1 wedge E3 wedge E4, E2 wedge E3 wedge E4. Where are all the rest? Well, they must be captured in here somewhere, right? I omitted anything that had the same basis 1 vector twice, and I only put permutations of these basis vectors that aren't redundant, in a sense. Okay, finally, how many basis 4 vectors? How many distinct ways are there of wedging together 4 different vectors in R4? Well, there's just one. I can wedge together E1, wedge E2, wedge E3, wedge E4. If I change the order, I'm only changing the sign. And if I repeat any of those basis 1 vectors, then I'm going to get 0. Okay, just one more, hopefully easy question. How many basis 1 vectors do I have? How many ways are there of wedging together just one thing? Well, I have 4 things, right? So the answer must be 4. How many basis 0 vectors do I have? How many ways are there to wedge together no vectors? Well, I can only do that in one way, which is to not do it. Okay, so I have 1 basis 0 vector. I have 4 basis 1 vectors. I have 6 basis 2 vectors. I have 4 basis 3 vectors, and I have 1 basis 4 vector. Do you notice a pattern here? Right? I have 1, 4, 6, 4, 1. What if I repeat this experiment for R3? Right? How many basis 0, 1, 2, 3 vectors do I have? Oh, I'll end up with 1, 3, 3, 1. So what do you notice? Maybe what you notice is that the dimension of k-forms in n-dimensional space is n choose k. Right? In n-dimensional space, I have n basis vectors, and I can only wedge together k distinct basis vectors to get a distinct basis k vector. Okay, useful little fact. Okay, we can use these basis k vectors now to get a more precise understanding of some of the objects we've introduced, like the Hodge star. So for instance, let's consider a 3-dimensional vector space with basis E1, E2, E3. How does the Hodge star act on basis k vectors? Right? If we can understand what the Hodge star does to basis vectors, we can basically understand what they do to all vectors. And the statement that's going to really pin down the Hodge star is this one, which is that for any basis k vector alpha, which is equal to ei1, wedge ei2, wedge ... wedge eik, we're going to define the Hodge star so that the determinant of alpha wedge star alpha is equal to 1. Okay? So intuitively, if we start with a sort of unit k-dimensional volume, then wedging together this volume with its Hodge star must also give a unit positively oriented volume. Okay? So to make this concrete, let's look at an example. So let's say we have alpha is equal to E2. Right? We're still in R3. Please find star alpha such that the determinant of E2 wedge star E2 is equal to 1. Okay? Well, in this case, it must be that star alpha is equal to E3 wedge E1, because then E2 wedge star E2 is equal to E2 wedge E3 wedge E1, which up to an even permutation is the same as E1 wedge E2 wedge E3. Okay? And by playing this kind of game, we can get a full list of how the Hodge star acts on all the basis k vectors. Right? Star of 1, just the basis for the scalars, is equal to E1 wedge E2 wedge E3. Star of E1 is E2 wedge E3. Star of E2 is E3 wedge E1, and so on. You get this nice regular pattern. Okay, so we start to get a more and more precise picture of exterior algebra and how it works. If you want a formal definition, here it is. Definition: let E1 through En be a basis for an n-dimensional inner product space V for each integer 0, blah, 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 blah. Please don't worry about this unless you really want to. Right? What we really want you to understand from this lecture is the concepts of k-forms and also the mechanics for actually manipulating and working with k-forms. If you'd like more formal definitions, they will be provided in your assignments. So just as a sanity check, just to see if we're all on the same page and we're following the basic concepts, try to answer this question. What is the difference, please, between alpha equal to 2e1 plus 3e2 and beta equal to 2e1 wedge 3e2? Are they the same thing? What's the difference? Okay, hopefully if you've been following along this far, you understand that one of these is a vector in the usual sense, and one of them is a two-vector. It's something that has this area and this orientation. Okay, these are different objects. Another example, really doing a calculation in a basis is, okay, let's say we're in R2 and we have a one vector alpha, which is equal to 2e1 plus e2, and we have another one vector beta, which is equal to minus e1 plus 2e2. Okay, so we could draw those as little vectors like this, alpha and beta. What is the value of alpha wedge beta? Okay, this is where it all comes together. Maybe you understand this conceptually, but can you really plug this in and do a calculation? Well, the best place to start with any calculation is to just take the symbols you have and make the substitutions that you know, right? So the very, very first thing we should do without thinking about what this means at all is to just swap out alpha for 2e1 plus e2 and beta for minus e1 plus 2e2. Okay, and now you really have to start thinking, right? What are the rules I have for the wedge product and which ones can I apply to this expression? Well, one we had nice pictures for was the fact that the wedge product distributes over addition. So I could break up one of these terms, let's say the second one, and say now 2e1 plus e2 wedge minus e1 plus 2e1 plus e2 wedge 2e2. I could then distribute again over the first term, and now I get minus 2e1 wedge e1 minus e2 wedge e1 plus 4e1 wedge e2 plus 2e2 wedge e2. Okay, stop, a little sanity check. What kind of object do I have on this line? Well, I have a sum of a bunch of wedges of pairs of vectors. In other words, I'm summing up a bunch of two vectors, and I started with alpha wedge beta, where alpha and beta are both one vectors, so I'm in good shape. I started with a two vector. I still have a two vector. Let's keep going. So at this moment, what can I do to simplify this expression? What other things did I say about the wedge product, geometric observations that I made? Well, one important one is that wedging any vector with itself is equal to 0. So I notice here I have e1 wedge e1 and e2 wedge e2, and those can both be set to 0. And so all I'm left with is e1 wedge e2 plus 4 e1 wedge e2. Okay, and now I'm in a vector space like any other. So if I have one copy of something and 4 copies of the same thing, that means I have 5 copies of that thing. I have 5 e1 wedge e2. Great. Sounds like a pretty satisfying answer for the end of the calculation. What does it mean geometrically? What did I just do? What did I just compute? Well, one way to say it, the pictures we've been drawing all along, is that I computed the area of this little parallelogram, alpha wedge beta. I know that that parallelogram has area 5, right? And I can also think about its orientation. It's kind of sticking out of the plane, if you like. Here's another example, this time in 3 dimensions. Let's say I have a 2 vector, alpha is equal to 2e1 wedge e2, and beta is equal to 3e3, and gamma is equal to e2 wedge e1. And so I have a 2 vector, a 1 vector, a 2 vector. Okay, more complicated example. What is star of alpha wedge beta plus beta wedge gamma? Well, maybe the first thing I should do actually is check that this expression even makes sense, right? So I said alpha is a 2 vector, beta is a 1 vector. That means alpha wedge beta is a 3 vector. 2 plus 1 is 3. Beta is a 1 vector. Gamma is a 2 vector. That means beta wedge gamma is again, a 3 vector, right? 1 plus 2 is 3. Okay, so that's good news. That means I'm adding together a 3 vector and a 3 vector. I'm adding together 2 volumes of the same dimension. Sounds pretty good. And then I'm going to take the Hodge star of a 3 vector in R3, and I should end up with a 0 vector, right? The complement of 3 in 3 is 0, and so the final result here should just be a scalar. Okay, so I have some sense of what I should get and that this makes sense. Let's actually carry out the calculation. And as before, the starting point is always to just substitute in the definitions of alpha, beta, gamma into my expression, and then apply all the rules. Yeah? So here I've done it. You can step through this at your own pace if you'd like, right? But I did all the things that you'd expect, making the cancellations to simplify the expression, and so on. And indeed, the final result is a number 3. So a good example to do at home if you're not feeling confident about these kind of calculations. Key idea here, by the way, is that in this example, it would have been pretty hard to reason about what's going on geometrically, right? I could have sat down and tried to draw pictures of these little 2 vectors and 1 vectors in R3 and these little volumes getting added together and so forth. I'm not sure it would have bought me much here. I really just wanted to carry out the calculation and get an answer. And so sometimes once you understand the motivation behind the rules, the algebraic approach is extremely useful for actually getting the job done. Okay. So just to summarize all the things we've said today, we introduced this idea of exterior algebra, and we said that this is basically a language for manipulating signed volumes in just the same way that vector calculus or linear algebra is a language for manipulating little arrows. Okay. Unlike linear algebra, length matters. We have a notion of magnitude always, and order matters. We have a notion of orientation. Otherwise, k-vectors behave like any other vector space. We can add 2 of them together, we can scale them, and so forth. The wedge product was analogous to the span of vectors, except that, of course, we have a magnitude and an orientation. The Hodge star is analogous to the idea of an orthogonal complement, though again, we have a notion of magnitude and orientation. And in 2D, we had a very important example that this really just looks like a 90-degree rotation. Finally, we looked at how to talk about exterior algebra in coordinates. So we can encode vectors in a basis. We can encode k-vectors also in a basis. And that basis is just the wedge of all possible basis 1 vectors. Okay, so that's it for today. Next time, we're going to talk about how to take measurements of k-vectors using something called a k-form. See you then.